Honor for me to share our latest multi-scenario recommendation work here. And the title of our work is the Scenario Adaptive Fine-Grained Personalization Network, Tailoring User Behavior Representation to the Scenario Context. And from the title of our paper, we can know that the focus of our paper is to explore the relationship between user behavior sequence and scenarios. That is, we want to tailor user behavior representation vector according to the scenario information, so that we can make sure even the same behavior will have different representation vectors when it occurs in different scenarios. Okay, I will firstly introduce the background of our work. As we all know, with e-commerce has evolved, commercial platforms accommodate various scenarios to cater to the diverse users' shopping preference. For example, we will take an international e-commerce platform, Lazada, as an example. In Lazada, there are many scenarios, like homepage scenario, my cart scenario, and my orders scenario. The homepage scenario primarily suggests a broad range of items potentially appealing to the user based on their past click behaviors, whereas my cart and my orders scenarios depend more on the user's historical purchase behaviors. So compared to the homepage scenario, user interest in the my cart and my order scenario will become more different from homepage scenario. Consequently, these multi-scenario e-commerce platforms will present a challenge to existing recommendation models. That's how to devise personalized recommendations that consider the distinct characteristics of each scenario. To model this into scenario correlations, mainstream multi-scenario approach often employ a unified recommendation modeling framework, but the traditional methods will employ scenario-specific data to train distinct models for each scenario. But this isolated model training approach is resource intensive and fails to capture inter-scenario correlations, so it will be sub-optional in data sparse scenarios. Up to now, there are main two types in this field. Like one is scenario-specific network structures. This type of method will use common network capturing into scenario correlations and separate networks modeling the unique aspects of each scenario. But these methods will require learning distinct network for each new scenario, so it's also complex. And the other method will be the scenario adaptive parameter network structure. They will apply scenario data directly to embedding and prediction layers, enabling dynamic adjustments in response to scenario shifts. But this method will transfer information between scenarios costly, because they will treat the user's entire historical behavior sequence as a single feature for adjustment. In fact, modeling user interest is quite critical in recommendation systems, particularly as users do not always reveal their intentions in non-search scenarios, making it essential to accurately track the migration of user interest for effective multi-scenario recommendations. For example, on the homepage, where user interests tend to be broad. Considering each click behavior within their historical behaviors is necessary to provide diverse recommendations. But in scenarios guided by specific interests, user may exhibit more defined preference. So it's very important for us to distinguish different scenario modeling. Here is an example for the previous methods. We can see that B1, B2 are the user historical behaviors, and the weight adjustment method uniformly applies the same weight to each behavior in the user sequence rather than tailoring scenario-specific information to individual behaviors. Thereby, this method will impair the model's capacity to accurately check user interest shifts across scenarios. Later, the SARnet ever attempted to incorporate scenario information into sequence modeling using a target attention mechanism. However, this approach of weighted summation does little to alter the actual representation of the user sequence because they only multiply a weight on each behavior. It's not enough. Therefore, adaptively and reasonably adjusting the representations of user behavior to match various scenarios remains an urgent challenge in contemporary multi-scenario modeling. And that's why we propose our method. In our approach, as the figure C shows, we mitigate the above challenge by tailoring the representation vector for each behavior based on the context features and the scenario information. To more effectively model the traffic interplay between user historical behaviors and scenarios, we propose the SFPNet. It's built from stacked block, and this block will comprise two modules, SAM and RTM. To make it easier for everyone to understand our work, so I will not show the formulas in our work in the following introduction. I will only introduce the general idea of our method. Here is the network architecture of our work. So we can see that we will use embedding layer to embed each feature, and all features will go through the scenario tailoring block, which is also the most important part in our work, and we will conduct the final prediction. Here I will introduce a detail of the scenario tailoring block. First of all, given the scenario information of the M scenario, we will have devised a getting function that applies scenario-specific adjustments at the instance level. Instance means a sample. Tailored to each instance features, we will aid in the encoding of scenario semantics within instance feature representations. It's just like the previous work. It's named PPNet. It's similar to us. Previous multi-scenario modeling methods often differentiate features causally, thereby overlooking the intricate interplay of individual user behaviors with different scenarios. So we will leverage a neural network to facilitate interaction with context-aware features, producing a distinctive context representation vector for each feature, because MLP is also a very effective tool for feature interaction. And drawing inspiration from residual architecture, we propose that once contextual interaction information is acquired via the aggregation module, residual connection are employed to merge the original feature representation with its corresponding global interaction representation, thus enabling recording into a globally aware representation. After encoding the sequence, each behavior representation vector will be finely tuned in accordance with the scenario, and we will aggregate the sequence at this juncture can substantially enhance the model's proficiency in extracting users' interests across various scenarios, so we can get more great prediction performance. And at last, in the prediction layer, we will use DIN to compress our sequence because the articles focus on sequence representation is not our primary purpose. Subsequently, we will leverage the benefits of a multi-tower architecture by incorporating scenario-aware DN tower set the prediction stages, and in this way, we can get the final prediction. At last, we will conduct extensive experiments to validate the effectiveness of our proposed work. Here are 4 questions, and we will answer them. First of all, we will answer the question 1. Here, in table 3, we show the prediction performance on the industrial dataset, which is collected in the Lazada platform. From the results, we can see that our model can outperform all baselines, indicating that the scenario tailoring block we propose can lead to prediction performance improvements. And nextly, we will answer the question 2. Here are 2 pictures, and in the picture, the white box representing improved performance when employing joint modeling as compared to separate training. And this finding underscores the importance of leading edge data from various scenarios for recommendation tasks, and also validate our multi-scenario structure design's ability to effectively transfer knowledge between scenarios. And here we want to answer the question 3, the performance of 5 variants on the industrial data. The results suggest that the performance drop from removing either the residual tailoring module or the scenario tailoring blocks is quite comparable. It also underscores the significance of our residual connection. In brief, the residual connection is quite important for us to tailor users' historical behaviors. And here shows if we change the number of stakes potentially enhancing its capacity to model scenarios, but limited by the dataset size if we add too much stakes, it will also make performance degrade. And here is the conclusion. To our knowledge, our work is the first multi-scenario work to offer fine-grained scenario-specific customization for individual user behaviors, and it's also comprising 2 key modules, which we can make more great prediction performance on all scenarios. Okay, that's all. Thank you.
Let's thank Moyu for the speaking.